Welcome to part 2 of my continued fractions presentation. Last time we covered what exactly were continued fractions and how they could be generated. This time, let's get our hands dirty and actually start doing stuff with them. And we're going to see how they're used in mathematics in general. So let's get started with one of our very first uses. Okay. The first major use of continued fractions is finding an approximation to irrationals. You may be wondering, how exactly do we find an approximation? Well, let me show you. Remember from the last part that all irrational numbers have an infinite simple continued fraction, like this, right? We obviously cannot evaluate every single term. It's like trying to figure out the sum of an infinite sequence by adding up all the terms. It's not possible. Instead, what we have to do is we have to truncate the continued fraction, aka evaluate only the first n coefficients. And whatever the value of that continued fraction is, that is the approximation to the irrational number. And the more you evaluate, the better the approximation you should get. Okay? So that's the whole concept. Now, how do we evaluate this continued fraction? And at first glance, it's not immediately obvious, right? If we use BODMAS, right? We have to start from the bottom to calculate the denominator. Then we move up, calculate the next one, a of n minus 2, a of n minus 3. And we keep going up and up and up until we reach the top. There are a bunch of problems with this. You can't use the previous convergence to get the next one because the denominators will change each and every time. It's very time consuming and it's very, very hard for computers to do. So it seems like we're at a dead end. Or are we? As it turns out, there's a formula. This is the most important formula in all of continued fractions, and it is known as the fundamental recurrence relation. Why? Because it is a recursive algorithm. Here we go, and here's the algorithm right here. Let a of n over b of n be the value of this continued fraction from a naught all the way up to a of n. This means that a of n over b of n is the n plus 1th convergence, just for the sake of notation. And a and n and b and n are just separate integer sequences that we calculate separately. And I'll show you how we calculate them like this. So, these two are the main statements. A of minus 1 equal to 1 and b of minus 1 equal to 0. A0 is equal to a naught and b0 equal to 1. Those are our base cases. Those are our initial conditions. You'll always see this when there's a recursive sequence. And as it turns out, for all n bigger than or equal to 1, you have this following recurrence relation. A of n, capital A of n, is lowercase a of n minus 1 plus a of n minus 2. And b of n is a of n b n minus 1 plus b of n minus 2. So they're the same sequence, except they've got different initial conditions, right? This is the formula, and as it turns out, it is always true for any simple continued fraction. In fact, if you are interested, I will actually tell you proof by induction of this following formula that applies to general continued fractions. It's the same base cases, except you add the numerators along there as well, next to a n minus 2 and b of n minus 2. I have a proof by induction for this. If we have time, I could go over it with you. For now, though, let's demonstrate why this is true with a classic example. Let's approximate square root of 2, yeah? You guys remember what the continued fraction, the simple one, for square root of 2 is? Hands up? Yep.
It's like 1 plus 1 over 1 plus 1. Is that one?
Oh, that's a golden ratio.
Okay,
How about the square root of 2? You're close though. Yep.
It says 1 plus 1 over 2 plus 1 over 2 plus 1.
Correct. That is the continued fraction. It's 1 and 2 to 2 to 2 to 2, so on. That's a continued fraction. Now, this is where you guys are going to bring out your calculators. We are going to calculate the convergence together. I'll start off with a couple of examples. So, this is the first step, the base cases rather. Then the next step is, as you can see in the top corner, I added the recurrence relation for you. We can calculate the second convergent, like this. It's just 2 times a naught, which is 1, plus a minus 1, which is 1, that's 3. And you can do the same thing with b1, you get a second convergence 3 over 2, which is 1.5. And then, one more example, a2. Now it's just 2 times a of 1, which is 3, and plus a naught, which is 1, so you get 7. b2 is 2 times b1, which is 2, plus 1 is 5. So the third convergent is 7 over 5, and you get 1.4 as decimal. Now, using the same inductive formula, what do you get for the next convergent of square root of 2? Yeah, so the denominator is right, Cyrus. The numerator is actually 17 over 12. And this is like the step, you do 2 times 7. Because that is the next coefficient, that's where these 2's come from, times 7, and then add 3, you get 70. So what's the next conversion?
41.
Yep.
29.
Yeah, well done. 41 over 29, that's the next conversion. Alright, what's the final conversion on here, which I'll show the next one?
70.
Correct, 99 over 70. Well done. Now, you guys must have typed this into your calculator, right? The decimal versions of these fractions. What do you notice about the decimal expansions of each of these fractions? Exactly. So you can see now that my formula seems to be correct so far. And if you keep doing this forever and ever, you will get square root of 2. We say the limit as n goes to infinity of the f convergent is square root of 2. And this works for any simple continued fraction, by the way, so long as you know what is the irrational quantity the continued fraction represents. Alright, let's see how good are these convergents, right? I created a little graph over here. I included square root of 2, which you can see the like blue line over here. I included the rest of the family because square root of 2 is quite lonely. I included the first square roots of numbers, non-square numbers, from 2 to 24. Okay, these are the continued fractions. What I've done is I've calculated the decimal value of the f convergent, and I checked how many digits match with the actual value of the square roots. For example, if the convergent is 7 over 5, which is 1.4, there'll be 2 correct digits, and that'll be the value of the y-axis. Now, what do you guys notice about this graph? Well, it's linear, right? When you double the amount of convergence you're evaluating, you get around double the accuracy. This means this is a pretty good algorithm for evaluating continued fractions. However, it's not the best. If you guys are aware of Newton's method, it's actually got quadratic complexity, meaning that if you just do one more iteration, the number of correct digits actually doubles. So it seems subpar, right? It doesn't seem so useful so far of approximating square roots when there are other methods like Newton's method available. But there is something really, really cool over here, which you can't see with Newton's method. There's a special property behind these rational approximations. They are the best. I'm not kidding. They are actually the best. This is a mathematical thing. A rational approximation, P over Q, is defined as the best approximation to a rational quantity when for all P prime over Q prime, with Q prime being positive and being less than Q, and when they're distinct as well, you get a difference between a rational quantity and P over Q is less than the distance between P prime and Q prime, meaning that each fraction you have is the closest possible fraction to the irrational quantity for any denominator between 1 and the denominator itself. And as it turns out, all convergence from the simple continued fractions that approximate any irrational quantity, not just square roots, are the best possible approximations. To demonstrate this, let's go back to our square root example and looking at the sixth convergent this time. So, if we want to try to do better than 99 over 70, which seems like a fair challenge, you can try. I have 3 attempts over here with denominators less than 70. I only get like 2 or 3 digits. There's no way I get like 5 digits. I recommend you guys try out these digits and try to prove me wrong. Turns out, for any denominator between 1 and 69, you cannot do any better than 99 over 70. Yeah?
So 99 over 70 goes to point 2a.
Yeah.
If you found one that ended in 3, would that be arguably better?
Yeah, that would. But as it turns out, again, you will never actually find that. Which is why I wanted to experiment. The next best one is like denominator above like 100 or something. So yeah, next one.
How does it prove it?
Okay, to prove is a little bit beyond the scope. The way it works is actually mathematically defining what the best approximation means. You can prove that an approximation is best when it's within the error of 1 over 2 times the square of the denominator. And you can show that all the continued fraction approximations really do satisfy this property, so they're the best approximation. But proving the first part of the statement is a little bit tricky in itself. Alright. Anyway, so that's pretty much it about evaluating continued fractions. there is one more thing about these special convergence, right? They actually solve Diophantine equations, and the most famous one being Pell's equation. Honestly, Pell's equation's got so much flavor and so much stuff, they honestly deserve their own presentation, to be honest. If you guys would like a presentation of Pell's equation, I'm more than happy to do one. Anyway, just as a little introduction, this is Pell's equation. X squared minus n times y squared equal to 1. Okay? N is any positive non-square integer, x and y must be positive integers, we look at positive integers only, and it must equal 1. Okay? Makes sense. Now this seems unrelated so far. But, as it turns out, all solutions x and y are convergence of square root of n. And what I mean by that is if you look at each convergent in its simplified form, x is the numerator of each convergent, and y is the denominator of each convergent. Like this. Remember that the second convergent is 3 over 2 for square root of 2 in this case. And you can check that 3 squared minus 2 times 2 squared equal to 1. Same equal to 4th, and same equal to 6th convergent. Now, I want you guys to figure out something for me. What about the other convergence? What do you get when you try doing like 1 squared minus 2 times 1 squared? And similarly for 75 and 41. You always get minus 1. Isn't that really, really cool? And let me tell you this statement in bigger detail as to why that happens. There's a little caveat here. You guys must have seen this arrow, right? It's only one direction, okay? That's the major problem. When I have a Pell equation, I know for certain that every single solution is a convergent, but I don't know which convergents are actually solutions. I have to find them out myself. There is actually no good way other than evaluating certain continued fractions. So it's not an if and only if relationship. And in fact, one could show, again the proof is a little bit beyond this Math Society presentation, that if square root of n has this continued fraction in this form, and I'll show you why it always has in this form briefly, the first solution, which is the smallest solution for x and y, is at the kth convergent if the period has an even number of terms, and a 2kth convergent if the period has an odd number of terms. Not only this, but you can only ever find the solution at the end of each period. Okay, and that is always plus or minus 1. Again, I'm not going to show you why that's true. I'll give you a live demo instead, just to demonstrate this cool fact at hand. With an example. We looked at n equal to 2. How about n equal to 61? Now this is like a proper challenge, guys. I'll give you like 1 to 2 minutes. Try to find the smallest positive integer solution to this equation. Go. Use your calculators. And whoever finds the first solution first gets £10.
Really?
Yeah, I'm serious. Go on, man. Go on, solve it. Come on. Yeah, but I'm trying to find you the smallest solution. Smallest.
Is that a fraction or is it a solution?
Yeah, to find integers x and y. Guys, I think I'll leave it there. I'll let you guys keep finding it. Okay. Alright, guys. Can I shock you for something, right? The first solution, the smallest solution is, drumroll,
61.
this! That's the smallest solution to this equation. And when I mean smallest, I mean smallest positive integer solution. You cannot find anything smaller than this. Isn't that unbelievable? And when I first looked at continued fractions, this fact blew my mind, honestly. There's no way that could be true. And it doesn't even look like, why is that true? Okay, yes, the continued fraction is quite long, but the coefficient is quite small. Even if I had a 20-second convergent, it should be quite small, right? Well, that's why I created a Python program to find it out. I'm not going to explain the Python program. Can everybody see this okay? Or should I zoom in? Okay. Yeah, so one of my biggest inspirations for this project was actually building my own continued fraction square root module that calculates continued fractions. I'm going to verify what the statement I just said in 2 ways, the continued fraction and the brute force method. So, I'm not going to go through my code. If you're interested, I'll send you the code and tell you more about it. Let's run it and see what happens. So, okay, this is the continued fraction method, and as you can see, that's a continued fraction I've used. And I evaluated the convergence of its continued fraction. And this is just the values of x squared minus 6y squared each time. Notice how none of them equal to 1 so far. and I only ever approach 1 when x equals to this and y equals to that, which is the same as on the board. Now, this isn't really convincing, right? Could there be another smaller solution that's not a convergent? Would you guys like to find out?
Yes.
Alright, so continue to naive brute force. This just works by iterating over every y, determine the value of x squared, check if it's a square number. If it is, we found a solution, we stop. Alright, so let's continue. Anyway, this will take quite a while, and so I'll actually come back to this at the end and see what the output of this program is. Yeah. Is it on? Yes, it's on. Okay, let's move on. And by the way, this is just an interesting little aside for you. You can check out the numerators and denominators of each conversion to square root of n by looking at the online encyclopedia of integer sequences. It is super duper cool, and it contains a lot of useful sequences in continued fractions. And as you can see, my solutions are right there in the blue rectangles. Anyway, that's Pell's equation for you. There's a lot more to do with Pell's equations that I couldn't cover, but this is the continued fraction side of Pell's equations. Here's the third use. Proving irrationality of certain numbers. We might take this for granted, right? Pi is irrational, duh. But mathematicians for millennia could not prove that. The ancient Greeks suspected it was irrational, but they couldn't actually formally prove it. The first ever proof that pi is irrational uses continued fractions. The very first ever proof. Let that sink in. First ever proof. And the best part is, it's easy enough for me to explain you the proof. I can literally go through the proof right now, which is what I'm going to do. The author of this proof is Johann Heinrich Lambert in 1761. Those who have heard of the Lambert W function, yeah, that's the same guy. Yeah. Alright. And this is his proof. Well, Lambert was like, well, I've got this continued fraction over here. Here's what I notice. Right, if x is rational, okay, because it's an infinite continued fraction, then I can see that as long as x is not equal to 0, and as long as x is rational, tan x must be irrational, right? It's an infinite continued fraction with no nice periodic properties. Okay, so here's how we're going to do this, right? Let's assume, by contradiction, that pi is rational. Well, that means pi over 4 is also rational, and I can substitute pi over 4 into here, tangent of pi over 4. And I get this infinite continued fraction. As we assume pi over 4 is rational, tangent of pi over 4 must be irrational by my assumption. But what is the value of tangent of pi over 4, guys? 1. And is 1 irrational? Contradiction. Pi is irrational. That's the proof. Isn't that awesome? Yeah. The hard part of the proof is proving that this actually is the continued fraction of tangent of x. I won't prove it, it's a little bit tricky, but I will demonstrate it. This is a proof by demonstration. And welcome to Desmos. Oh, I need to stop the slide. Yeah, you guys see it? Alright, this is the Desmos graph. Inside this third folder, I've defined a continued fraction using the recurrence relation formula, generalized version earlier. You can see like the base cases. The formula is a little bit of a mouthful. Yeah, you just gotta trust me that this is the continued fraction. This red line is tangent of x, and the purple lines will be the approximation. So as I evaluate more and more continued fraction, I should get something close to tangent of x. Let's find out, shall we? Here we go. You want me to do it slower?
Yes.
Yeah.
Alright. In fact, just one thing to go. Already by like the fourth convergent over here, as you can see, at least from negative pi over 2 to pi over 2, this continued fraction is basically equal to tangent of x, right? So, and we keep going, it just gets better and better and better and better. Also, interesting thing to note, right, is I added a little Taylor series comparison, where I used the Taylor series of tangent of x. I would like you to compare how good a Taylor series is. Okay, I need to like show the graph. What do you guys notice about a Taylor series?
Only in the range.
It's only restricted to a range. And that's in fact one of the main benefits of functional continued fractions, is they often work over a much bigger range of values. If you guys want to fiddle with this, I'll send you the Desmos graph and you can explore it on your own. Isn't that pretty cool?
Yes.
Yeah.
Why does the Taylor series work a bit?
It's because of the Bernoulli numbers. They're kind of a mess, but yeah. All right. Anyway.
If you order restricted,
All right. And so those are the major uses of our continued fractions. Let's look at some specialties. Okay. The first thing is, what do you notice about the square root of n? I've shown you on the graph earlier. Here are the continued fractions in square root of n. Any patterns you guys might notice? Yep. Yep.
There's no 7 plus.
There's no 7.
Or 9.
Yeah.
There will be a 7, but yeah, you're right, based on this series. What do you notice about the first term?
The floor of the number.
The floor of the number? What about the last term?
Floor of the number squared.
Double it, yeah, you double that number. And what is interesting is that the period always starts at an index offset of 1. And if you actually cover the first and last term, you get a palindromic number in the middle. You get a palindrome, always. I can't prove most of these properties for you, but some of it just pop straight out of the process, like the first term and the last term. But yeah, it's pretty cool how there are some really nice, elegant patterns. And there's a bunch of little party tricks that I've got on here. This is like an alternate way of deriving the continued fraction of the golden ratio. We can start with this quadratic equation, and we can then set it equal to 0. We can move the terms to the other side. You get x is equal to 1 plus 1 over x, which is its definition of golden ratio. We can then do this replacement over and over again. So you get x is equal to 1 plus 1 over 1 plus 1 over x. Do this again, you get 1 plus 1 over 1 plus 1 over plus 1 and so on. And therefore, you get the golden ratio is equal to 1 repeating on and on forever. This trick only really works with like really nice numbers that got really good quadratic equations. As far as I know, I can't really see a way to get negative numbers just yet, but it works pretty well for stuff like golden ratio. And also, you can do this trick in reverse, actually. I could give you a periodic continued fraction, and I can tell you what the value of that is by looking at it right here. Where's the periodicity, right? Well, to reveal it to you, I'll have to split this continued fraction, this 6 rather, into a 3 plus 3. And what do you notice? The continued fraction inside the blue box is equal to the original, because it's 3 and 6 and 6 and 6. It's also equal to x, so we can substitute it back in. And then you get a quadratic equation. Well done. And what is the solution to this quadratic equation?
plus 1 root 10.
Yeah, but it cannot be minus root 10, because if you look back at a continued fraction, it's always positive.
Yeah, it's always added.
Therefore, x is equal to root 10 over it. Yeah, it's always adding and all the coefficients are positive. Isn't that awesome? And by the way, guys, this is basically Euler's proof about the reverse of my cool property that if you have a periodic continued fraction, it's always a quadratic irrational. The reason is because Euler proved that you always get a quadratic equation if you do this process, which is pretty awesome, but the rest of the technical details are a bit time consuming. I've just a couple more things before you guys go. This is the continued fraction of pi. And it's a simple continued fraction, at least. It doesn't look like that's like a nice pattern, right? But there is one thing really elegant about this continued fraction. Yep?
That's an approximation to pi, right?
Yes, these are better approximations than pi. And that is true. But what is really, really special is that is actually really, really good approximation of pi. They all are famous approximations of pi, like 22 over 7, and 355 and 113. But the fact that this coefficient is so large, that actually means that the previous coefficient, previous approximation rather, is a really, really, really good one. And this comes straight back from the original process of generating this continued fraction. Isn't that awesome? So just a little bit of trivia. It's such a good approximation to pi that it's known as a Zhu-Chongqing fraction, named after the Chinese mathematician who first discovered it. So this continued fraction proves that 355 over 113 is the GOAT of pi approximations. Right there. And these are like alternate continued fractions for pi. They are general continued fractions. They've got really, really nice properties. These are the odd square numbers. They get 3, 6, and 66. 4 over pi is again odd square numbers of 1, 2, 2, 2, 2, so on. And they actually come from the Wallace product, by the way. It's like pi over 2 is 2 over 1 times 2.
Do you know how you prove that?
How you prove that? I'm not sure. I can't really prove it to you to get a little bit beyond this, but you can prove it by. You can prove it though because there's a way of transforming various continued fractions. Because I'll show you right here. This is the simple continued fraction of e, As you can see, it's got a very, very nice pattern. It goes 2, 1, 2, 1, 4, 1, 6, 1, 8, 1, 10, and so on. Yeah. And you may be wondering, why is there that nice pattern? It's because of Euler's formula. That answers your question. That's how you could derive like continued fractions from a bunch of Taylor series and a bunch of product sums even. Euler actually proved the top equation by induction, and this actually comes with a continued fraction of e to the x. So basically, Euler could convert a Taylor series into a continued fraction, and that's how you obtain a continued fraction of e. Is that really awesome? And that right there, my friends, is the end.